Okay, in this video we're going to talk about a repeated measures analysis of variance and how we partition and break up the variance. So it's the same example that we used before. So same levels of caffeine, same data and everything, and same measurement, dependent variable. So the difference is we're now treating this data like we collected it from the same subject. So subject 1 was tested under this condition, subject 1 was tested again under this condition, and subject 1 was tested under that condition. Same for subject 2 through 5. So really there's only 5 people that participated in this study, but they were tested 3 different times. So we end up still with 15 data points, but only 5 subjects in it. So when we look at the formulas, sorry about that, when we look at the formulas and the source table for repeated measures analysis of variance, it's very similar to the one-way analysis of variance, but you'll notice that we have an additional entry. Before we only had 2 entries. We had a source of variability which was due to our independent variable. Here I'm calling it factor A. Factor is an independent variable. So this is due to our independent variable. And you'll notice the degrees of freedom are the same. Number of groups minus 1. We have a formula for calculating the sum of squares. I'm calling it A here for factor A. And we'd have a mean square, which would be the sum of squares divided by the degrees of freedom, right? So that's the same. We also have a total. And the total is, we have the degrees of freedom, sum of squares for total. That's all the same as well. What's different is now we have a source of variability which is due to our subjects. Because we're testing all of the same subjects multiple times, we're able to sort of see how each subject varies from each other, right? So if subject 1 was really slow, subject 1 is going to be slow across all 3 conditions. And so what we could do is we could average across all of 3 of these conditions and form a value for the subject 1's data and compare that to subject 2's data. Subject 2 may be faster for reasons that we have not manipulated, explored, or controlled. People are just different, individual differences. And what we can do is we can calculate the subject variability here and effectively take it out, account for this, take it out of our analysis of variance. And what that does is it makes this error term, which is still the same, a little bit smaller. And really, in reality, and I've indicated it here, it's how the IV interacts with this individual subject variables. It's how each individual reacts a little differently to our dosage level. That's what we cannot explain in this particular case, because we can't explain some of the subject variability. So what this means, if you compare this analysis of variance, so here's what we did the same analysis on the same data as in the first example. What you'll notice is that the error term is much smaller. So look at here, it's 39.97, and just for comparison, I'll scroll up, and up here, the error term was 666,133, and everything else is the same, right? Everything else is the same, and our F value, of course, gets a lot bigger, 588 versus 35, because that denominator is smaller. That denominator is smaller because the subject variability was taken out of the error term. It was removed, it was accounted for, removed, and discarded. Now the thing is, SPSS will not show you that subject variability unless you do some tricks and add some commands to have it produced. But generally it's hidden from your view, which is sort of indicates here. And of course we have to adjust our eta square calculation as well. A couple terms there. So the repeated measures analysis of variance is very similar to the one-way, except you have subject variability calculated and removed from